So multi-agent problem is very simple, is when you replace one robot by several agents.
This is Hadrien Hendrikx, a PhD candidate at Inria Paris, who did his master's at EPFL. During Hadrien's master's, his collaborators Rachid Gheraoui, El-Mahdi El-Hamdi, Alexandre Maurer and himself published an EPS paper on safe interruptibility for multi-agent learning AI systems.
Instead of having just one, you have 2, 3, or even plenty, and they interact with each other. They all live in the same space, they all observe each other. And more critically, the outcome and the rewards they get depends on the action of everyone. So it depends on the joint action. It's not, they don't live in isolation in the same world. They really, there is interdependence between the agents. So that's the basic multi-agent setting.
So what does it change in terms of interruptibility?
In terms of interruptibility, it changes quite a lot of things, because so I've said that the main thing allowing safe interruptibility to work was off-policiness.
We discussed off-policy in a previous video, but just as a reminder, what is the off-policy property?
The value of an action in a certain state for the robots in off-policy algorithm, it will just depend on the action. So on the action and on the state.
Let's illustrate this with learning agents exploring a landscape.
So they will say, if I'm on the verge of a cliff, I can look at the view and it's magnificent, and I can do the action stare, which will give me a fantastic reward because I really like that. So this would be what an off-policy agent would learn, and an on-policy agent, on the opposite, would learn that when I'm on the verge of a cliff, so you can imagine the agent as a baby, my parents will come and just take me away because they think it's dangerous, and so I'm not going on the verge of this cliff anymore, because I know it's zero reward, because I just get pushed away and they punish me afterwards. So I won't do that. Even though I know that there is this staring action that really would give me a very high reward, I will not do it, because I know that the following action I cannot choose it. My parents would choose it instead of me, or my supervisor would choose it instead of me. And so that's really the main difference between the two.
Why is interruptibility trickier for interacting learning agents?
The problem when you have several agents is that since the action of one agent depends on the actions of the others, then you can have the same kind of phenomenon where an agent will say, I will not go to that state because I know that this one always acts the same, and I know that if he acts like that, it's not worth it for me to go there, and since he always does that, well, I just won't go. And that's problematic, because it means that you need some degree of communication between agents. Even if each agent has itself an interruptible policy, if it is not able to see the action of the others, if it is not able to recognize that there are other agents in its world, then it will learn to react to the behavior of the other agents, and so to the interruptions of the other agents.
So what do we need for safe interruptibility of interacting learning agents?
This means that you need some kind of communication, because in the multi-agent problem, agents do not necessarily have to know that there are other agents and that the other agents are the same as them, that they have actions, they learn stuff. It's just an environment for them. And you actually need to add these assumptions. You need to specify the agents that these other things in their environments, they also act according to some laws, and sometimes they can be interrupted. And when they are interrupted, you should not take their actions into account. Or the other way around is to actually break the multi-agent component. They do not put a value on their own action, but on the actions of everyone. And so they can communicate or apply rules to take the actions which is less risky compared to with all possible actions of all other agents. But here you kind of break the multi-agent aspect, because it's actually just a centralized agent, as if there was someone over all the agents that was taking the decisions for them. So these are really the two, but in both cases it implies that you need some kind of communications. The complete isolation, even with safely interruptible agents, does not work.
So to recap, interacting learning agents are even trickier to safely interrupt, because any interruption of one agent is likely to affect the learning of another agent. To guarantee safe interruptibility in this setting, a communication protocol between agents seems critical, but arguably much more work is needed.
So as I said, it's a very new field. The first paper was published in 2016, or it was the year after, and this is mainly because the definitions that were used for the single agent case were not well suited to the multi-agent case, because they needed notions of convergence. They not critically, but they kind of relied on the fact that there was an optimal way of taking actions for the agents, and that the agent would converge to this optimal state. And when you have several agents, it's not necessarily true, because they can co-adapt. It can influence all the time, and if one agent starts to change its actions, well, all the other agents will react to this change. And so it has been shown that even if there are some equilibria situations, the most learning algorithms are not guaranteed to stay in this equilibria. They are guaranteed to play most of the time, and even like arbitrarily often, the equilibria situation, the equilibria plays, but not all the time. And this was a problem, and so we proposed a new definition that was more focused on stepwise dynamics, and that allowed to apply safe interruptibility to this system.
We first redefine the concept of safe interruptibility in a multi-agent system. Then we consider the case of reinforcement learning for joint action learners. We show how such a system can be made safely interruptible. We then consider the case of independent learners, which is, well, more complicated. But we can still achieve safe interruptibility by adding a pruning mechanism.
The problem with reinforcement learning as a learning paradigm is that you create artificial intelligence whose objective is a bit scary. Get as much reward as possible.